Let's get started. Well, hello everybody. So thank you for joining us again for another webinar of our center. Again, we have two very valuable speakers today with us, and they're going to talk about the research that's being done under the center, one of them, and the other one is related to the Missouri Center for Transportation Innovation. So our first speaker is Dr. Gardiner. Dr. Gardiner is currently an assistant professor in the Department of Civil and Architectural Engineering at Tennessee State University. And she received her PhD in environmental engineering from Vanderbilt University after serving as a regulator and environment consultant in California, Colorado, and Tennessee. Her professional experience includes designing groundwater remediation systems at oil and gas and Department of Defense sites, and designing landfill structures and performing compliance work and aiding in diverse stakeholder engagement. So she brings a lot of experience in this area. So without further ado, I'll let her start her presentation.
Thank you very much. I appreciate it. And thank you for joining us today. Today, I'm going to talk about the evaluation of green infrastructure as a means to mitigate increased stormwater volumes in disadvantaged communities. So I'd like to acknowledge the funding for this project was received from ETRC3, and I'd also like to thank my students at Tennessee State University. Seskar Kangogo was a graduate student on this project, and Michaela Purvis and Andrew McHale were undergraduate researchers who participated in the development of the research or the data for this project. So just to kind of frame where this work came from. So, in the past 2 decades in particular, we've seen these incidents of extreme rainfall occurring, and they're increasing. We're seeing them more recently. And even from the time this work was done, additional events have occurred. So, for example, we have hurricanes and extreme storm events that are occurring. Sometimes they impact regions that are quite near to the coast. So for example, Hurricane Harvey in the Texas, Gulf of Mexico area, Superstorm Sandy impacted the New York, New Jersey area on the East Coast. But I just added Hurricane Helene to this in 2024. We saw impacts of a hurricane in Florida that caused flooding issues in North Carolina and East Tennessee. And for example, also in 2022, a non-hurricane event that happened, but extreme rain event in Missouri, Arkansas, and Illinois, Indiana, and Kentucky saw over 8 inches of rain in a very short period of time. And so, for example, Lambert Airport in St. Louis saw 25% of its annual rainfall in 12 hours. So these events are quite impactful. And I wanted to just show a couple pictures from that. What these rainfall events are impacting are communities, in particular near transportation corridors. You can see light rail systems impacted, highway systems impacted. And so it's just not only transportation, but also just these flooding events that are occurring. So flooding is a natural hazard. It happens with a lot of social and economic impact to the United States. These frequency intensities of storms are also causing these flooding events to increase. It's impact of many things, these excessive rainfall events, increased urbanization, loss of green space, and also the undersized stormwater management systems to move this water away. They are escalated in transportation corridors in particular. They're absolutely impervious surfaces that flooding occurs with. And when this flooding happens, it's harmful to human health. It transports pollutants, cuts off access to utilities and emergency systems and transportation. So in the built environment, what stormwater management looks like, well, we have, urban areas, they're built up, right? We have roads and buildings, less green space, no infiltrations happening when we have those impervious surfaces. This building of the environment, and I'm sure everyone on this call lives in a city where there's been impact to growth. I'm in Nashville, Tennessee. We've definitely had a huge impact to our green open space. We have this change in runoff, right? So things that may have been mitigated before, you can see the NRCS curve numbers. Impervious areas are much higher than grass areas, which correlates to how much stormwater we're going to see. So if we have too much water and our systems can't manage it, we're going to have flooding. Now, I just wanted to show 2 figures, and this first figure is showing where flood risk is projected to rise fast in the United States. And I've circled a couple areas. I have Louisiana, Florida, and that New Jersey, New York, kind of upper Atlantic, mid-Atlantic area shown. And the areas of dark blue in particular are where we expect to see increased flooding. On my next figure, I'd like to show you where we have this overlay with vulnerable communities and why these stormwater issues are so important for us to consider. So as you can see in Louisiana, Florida, and New York, we have vulnerable communities that are having difficulty recovering from these extreme rainfall events, right? And we need to be mindful of this as we build and change our environment. So this research looked at disadvantaged communities who bear a disproportionate amount of a burden due to flooding impact, right? They tend to live near transportation corridors. We have a lot of cities like that. They tend to live potentially in floodplains, things of low elevation, maybe near water conveyance, whether rivers or stormwater. Also lack of green and open space, right? So they have this overlay is happening due to the built up urban environment, but also who lives in that environment. Why we see the transportation corridors having an effect on these communities? Well, after World War II, we had suburban housing developments started to grow and started to occur. And we saw those where it moved population centers further away from the city itself, from the urban core. These highways and transportation routes were constructed to connect the suburbs to the city. But what it did is it tended to impact communities of color or low income and ran highways through those areas, right? They weren't able to move out of the urban core. And these construction of highways also negatively impacted, the real estate. They were exposed to more pollution in the 1970s. There's a lot of discussion about lead air pollution, right, on these communities. And so we saw a big change to who was being impacted by these corridors. I just wanted to touch lightly on environmental justice. Obviously, that is a piece of this work when it was drafted. And we look at environmental justice is that there are people of all kinds of different, shapes, colors, national origin, tribal affiliation, disability, right, that EPA looks at for when they define this. So in particular, we have seen these environmental justice impacts to communities in Nashville. So for example, I-40 is an east to west highway. It runs actually very close to Tennessee State University, where I'm at. It was originally planned near Vanderbilt University, and many of you may have heard of that institution. It's a private institution just south of us at TSU. But they moved the highway north into this African-American community. You can see here we saw loss in property values. It actually cut Jefferson Street, which is a cultural kind of connectivity road. It cut it in half. It split neighborhoods in half. It also exposed these. So we've seen this in particular in our community. So the objective of this research was to determine where there's an overlay of disadvantaged communities and also impacts of stormwater. And so kind of seeing where are places we could earmark to look for in the future to implement green infrastructure. So the methodology behind this research was a couple steps, and I really appreciate the graduate student and undergrads that had the chance to work on this research. So we started by identifying extreme rainfall and flooding events in the United States. Where are these events happening across the 50 states? Then we looked at, for specifically, where did we have what we'd say a 24-hour, 100-year rainfall event? Why we picked that is because in engineering, 100-year rainfall, 24-hour means, every 100 years probability we'll see a storm like this. When we deal with engineering design, we tend to use this as the upper end of extreme design. A lot of things are 25-year, 24-hour rain events, 100-year, for example, stormwater structures. For excessive, we go to the 100-year. We also then looked at EPA's EJ screen tool to look at socioeconomic overlays with these areas where we saw these excessive rainfall events. And then we selected a few to talk about. And in future iterations, we're going to look at, green infrastructure selection. We're proposing for another round of funding from this research grant to look at, building some of these stormwater structures. And then also that we can make recommendations for green infrastructure. So like I said, we looked at location, date, amount. We also looked at classification of rural and urban because obviously those built environments will act differently. We looked only over the past 10 years to kind of keep it in this. Obviously, we recognize extreme rainfall events have happened outside of that. We started with looking at news articles and internet pages, not just necessarily the statistical probability from, let's say, NOAA, but also what was actually being reported and to kind of pinpoint some of these areas. And we specified data collection within that limited time. So as you can see from this figure here, we looked at the number of excess flooding and rainfall events from 2005, and it was to 2023. We saw 99 total, and you can see where they're kind of, the Southwest had very few that we found. And please understand with this data, there are more events than probably were captured here. This is just one slice of data that we collected. We can see the Midwest and the Southeast in particular had higher numbers, and the West and Northwest were kind of similar. Just to show you for Midwest, Missouri and Michigan were listed with the highest number for our study. For the Northeast, the District of Columbia and Maryland had the most reported. For the Southeast, we saw Louisiana and Kentucky and Florida. And I think surprising just from thinking of rainfall events, Louisiana and Florida are obviously ones that we can tend to think of because of hurricane impact. But to see that Kentucky had quite a number of impacts was very interesting, I think, and just kind of backs up some of that other information that we've seen. In the Southwest, we only had one reported for each. And obviously, like I recognize more events have happened than that, but that was just what the students found. And then in the West, we have Montana and Hawaii that had the highest number of incidents. So when we looked at this rainfall, as I said, we looked at the 100-year in a 24-hour period. It provides that balance between short duration. Short duration can be very high amount of rainfall. A rain shower comes through, and also longer duration storms. And sometimes there are 2-day, 3-day storm events that occur. But we chose this also because of that engineering design aspect to this. We looked at all this data and, for example, when we pulled these locations together, when we made up the master list, we saw that, for example, Graves County, Kentucky in 2021 received, 7.99 inches of rainfall in that event that was noted. When we looked at NOAA Atlas 14, which is the predictive model for these storm events, it showed that it was 138% greater than what was expected in a 100-year storm event. And also as these frequencies occur, and we're seeing that, I know Kentucky was recently impacted by flooding again, right? These are more than 100-year occurrences that we're seeing. So just to talk real quick about the overlay with the environmental justice screening tool is we looked at, there's many, many indicators within here. So environmental burden indicators, socioeconomic indicators, climate change, health disparity, and then critical service gaps. For this, we focused just on a few of these. Obviously, there's a lot more that we could look at, but we were interested in flood risk and then also some of those socioeconomic indicators. And so the 4 that we selected were income, people of color, and unemployment. And then that climate change indicator we looked at was flood risk. And then we found and averaged them in order to attempt to prioritize them. The cities that we chose to look at further, and of course there's more than just these, but the 5 that we selected was Santa Barbara, California, Maricopa, Pinal area of Arizona, Baltimore, Maryland, Jacinto City, Texas, and then obviously we looked at Nashville, Davidson County, which is in Tennessee and in our campus region. So just to show you here, this screen is showing some of the socioeconomic, and I've just got a couple of screenshots to show you, but this is how the mapping tool presents itself. And as you can see, the more red or darker orange it is, it's the percentile that's occurring. I also tried to point out here transportation corridors, and you can see, for example, I-895 is right along an area of red, and also less though 695 and I-95 is on there. So just to kind of show you some of that data. Jacinto City, Texas, that we looked at. Here you can see I-10 that runs through this area, and it's mostly 90-95%, and then some areas of 95 to 100% people of color listed in this area. Nashville, Tennessee, this is I-24 and I-65 and I-40. We have kind of a mix of highways that happen in that area. And you can see that we're at the 80 to 90% in these areas with some of these highways. And I do feel also, I know a lot of cities' demographics are changing as urbanization changes. Here's looking at Pinal County, Arizona. And so I-10 is kind of up We have I-8 in the area also, and you can see we have some areas of disadvantaged communities. So these communities are not only, have some of those socioeconomic indicators, but also that we have seen excessive rainfall events occur. Here's Santa Barbara, and Santa Barbara is kind of an interesting one. There's a lot of high property value, but the people, those individuals live outside of kind of the highway transportation corridor. So people, we're seeing some of those impacts, 50, 80, 95. Those people, those individuals are living along the transportation corridor and not up, and you can kind of see houses on that, right? Not up into the mountains. So the students pulled this information together to kind of look at the comparison of the flood risk indicators and socioeconomic indicators. And we saw in a lot of cases, we had a high flood risk associated with also, kind of a high economic indicators where the students kind of averaged those values together. And so we can see, for example, Baltimore, high for flood risk, and also along those transportation corridors, we have a lot of potentially impacted communities. So I just wanted to give the group an understanding kind of when we talk about green infrastructure, because one of the ways to manage these built environment is to implement green infrastructure. And we have a lot of different types that we can use, but I just wanted to introduce a few, and many of you may have seen these in your community or even in your own engineering design work. So for example, we have permeable pavement, which though you can see there are blocks that are solid, it has this permeable joint in it, so it's not cemented together, but kind of graveled in, and it allows water to infiltrate down. And you can see that picture on the lower left that shows, kind of the structure, but it has an underdrain. So what that means that instead of the water sheet flowing off the top and then, overwhelming stormwater structures, we can allow that water to infiltrate. And with that, as spatial, right? Rainfall is not only temporal, but also spatial. It allows for that water to be managed kind of more locally and then moved away from these areas. You can also see a picture of a bioswale there, right? We see those a lot in parking lots, for example, like they'll use that as a way to manage the water and allow that water to move off. Now, one thing we're not really talking about in this particular research, but that these structures also allow for treatment of water, right? Especially bioswales allow for pollutant removal. It was not part of our research, but I definitely wanted to point that out because I think that's an important part of green infrastructure, not just the water management piece, but also the ability to protect the environmental space. You can also see in that picture on the bottom, we have a constructed wetland, right? A wetland is, more than the bioswale just having some plants in it, it's mostly plant filled, right? And it allows that water to attenuate, to slow down, and also allows that ability for those plants to, use that water, mitigate that water, and kind of present, opportunities for preventing of flooding. So in particular, Nashville has some initiatives, Metro Stormwater, for, the implementation of green infrastructure. And so looking at their plan, they have things like green roofs, water harvesting, bioretention, biofiltration areas, water quality swales, permeable pavement. In the state of Tennessee, Tennessee Department of Transportation oversees the highway corridor. So Metro Nashville oversees, the streets and the surface streets, but TDOT oversees the highways themselves. And at this point, TDOT has no implementation of green infrastructure. So these areas that are potentially impacted from stormwater flooding for transportation corridors don't have anything above and beyond typical stormwater management. And so there are grassed areas that are kind of, undeveloped, but they're not specific to water mitigation. So I just wanted to show you some of where we have pinpointed for Nashville to look forward in further research where we can implement these. And you can see I-65 and I-40, and they spend a minute in Nashville kind of becoming the same highway over there. And we can see, for example, there's a 95 percentile, I-65, and then I-40, and Tennessee State University is actually listed over there to the left. We have this potential for flood risk in these areas. What I'd like to show you, so I'm going to look at this particular intersection of these highways, And when I show you this, right, they are just green open space with, overpasses is the highways connect to each other. And so, but no green infrastructure. So if those areas, especially down to the south, they could be potentially impacted from these excessive stormwater. And Nashville just got hit by storms, right? The same ones that impacted Kentucky came to Tennessee or came to Nashville. We see these excessive rainfall events. We don't really have the infrastructure in place to treat or to manage this. I also wanted to show you this other circle over here. This is Jefferson Street with TSU. And you can see here, once again, from the aerial photograph, right, we just have kind of green structures, and that's a very steep hill right there. There's really no mitigation until you get to the street itself. And obviously, stormwater structures on a street are not meant to manage the stormwater from the highway. There are also drains, surface drains along the median in that highway, but there's nothing on that green space. Let me show you just one more location too. We can see here, you can see kind of a water management structure, but once again, it's concrete, and it's not meant to attenuate or manage that water. So some future work that we're planning to do and we're proposing in the next phase is to really look at this ability to mitigate water along these highway corridors. So we're in the process of proposing to develop, looking at these engineered bioswales to attenuate water, to reduce this potential impact to these stormwater areas. And then also look at treatment, right? Because with our partners in ETRC3, we've seen a lot of potential environmental impacts due to roadways and transportation corridors. So if we can both mitigate the excessive stormwater with a natural engineered system, and then also treat, we have the potential to really improve water quality. And then also, as a recommendation on regional areas where we have these intersections, we can improve quality of life to anyone near a transportation corridor to be able to mitigate this water so that we don't have, because like I said, they're temporal and spatial. We can have rainfall that just happens in one place, very hot, in terms of intensity, I should say, not hot in terms of heat, but that it can potentially impact these areas. I'd like to thank the partners at ETRC3 for support of this project, and look forward to engaging with folks. And there's my contact information at Tennessee State University. And I thank you for your time today to listen to my presentation.
All right. Thank you very much, Dr. Gardner. Very nice presentation. And it's clear, your data shows that the connection between the transportation system and the high flood risk. So it is, and you talked at the beginning that the 100-year events are not really 100-year events anymore.
Correct.
So it's clear that we need to change our design parameters and think outside of the regular water management systems, and the ones that you're showing are going to be more effective in terms of managing the water and also cleaning it. It's treating the water. So
exactly, if we can prevent these from happening, it's positive to all areas, right? That all people, and not just roadways, but also railways and other transportation pathways, that we can also keep those services open in times of extreme. And if we're going to see hurricanes hit inland, right, with these extreme events, then we need to be cognizant of this to not have all our infrastructure wash away. Because I know, for example, I-40 here, I'm in visiting East Tennessee right now, and they're finally opening that piece of highway along I-40 that washed out during that excessive Hurricane Helene, which was back last year. So, also to be able to keep corridors open, right? I think we need to look more at how we can manage these not random, but these hot spots that are occurring.
So since you have a background in the Department of Transportation and Environmental Regulation, so how involved are these, like when there's a new project, when there's a highway improvement, new lane build up, or for safety measures, they're doing highway changes. How much of these new green infrastructures come into play? Is that something that the DOTs naturally look at, or is it always an afterthought? So
I think it's a good question, because a lot of highway federal dollars require NEPA, which is looking at impacts of, a variety of, there's a lot of categories that NEPA looks at. And I don't know in particular if green infrastructure has been looked at that, but I think that if we could tie that to the NEPA process and just show that there is, because that infrastructure will do a lot, right? Pollution removal and water management and loss of, damage to infrastructure. I think it's maybe something to consider or maybe just to encourage on front end design. If designs can come in with this. In some states, I had a student working, we haven't finished all the work, but just looking at the overlay of this research with all or this data with also states that do implement green infrastructure, because some states do. And here in Nashville in particular, state of Tennessee, Nashville has those plans, but I can't say that DOT has explicitly looked at that. So I think it's something in the policy to look at how we can, implement this and show also cost benefit, right? That we can implement these on the front end. But I don't think there's a connection with that highway design or transportation design and also that green infrastructure. I think we're in a good place to really encourage that and create those design spaces.
Right. And this data that you are presenting is going to help justifying those designs. Actually, it's very clear correlation between the flood areas and the transportation system. So thank you very much.
Thank
So,
you.
not seeing any more questions in the Q&A, so we'll switch to our second presenter. So Dr. Binbin Wang, and his title is Application of Simple Modeling in Assisting Freshwater Mussel Protection and Sediment Spills. Dr. Wang is an associate professor in the Department of Civil and Environmental Engineering at the University of Missouri. His research concerns fundamental fluid flows and how they impact the natural and engineered aquatic environments. Dr. Wang has led or co-led research projects in the excess of $3 million funded by various agencies, including National Science Foundation, U.S. Geological Survey, Office of Naval Research, Gulf of Mexico Research Initiative, and Missouri Department of Transportation, besides private funders. He was elected for 2022 Early Career Research Fellowship of the National Academy of Sciences Gulf Research Program, and he is an associate editor of the Coastal Engineering Journal. So without further ado, Dr. Wang.
Well, today I'll be sharing some of the research that we have done in the past few years and relevant to the Department of Transportation applications, especially regarding protecting freshwater mussels. So I'll be talking about this research with lots of collaborators and that put it on the screen. So as we all know, the freshwater mussel is really important for state of Missouri. The freshwater mussel itself has very strong ability for water filtration. It can improve water quality and cycling nutrients and energy. And for the stream, if you find a freshwater mussel, it's a good indicator of overall health of an aquatic ecosystem, and water quality is pretty good. And it's also an important part of food chain. And in the early days, it has a very strong economical impact for the bottom manufacturer jewelry industry. Okay. So this slide shows a map that published by Missouri Department of Conservation and shows a decline of Missouri mussel habitats. This is a pretty old data and prior to 1978 showing up in these brown dots. And you can see there's a blue dots, dark blue shows the data after 1978. And this decreasing habitats, and also there's lots of species has been listed either endangered or of the conservation concerns. And relevant to the Department of Transportation or any construction relevant projects. So sediment is a big, it's a big concern for the mussel habitats. There's all kinds of different engineering practices that could cause the elevated sediment, concentrations in the streams, which could impact the mussel habitats. And in this particular project, we are interested in, the point source sediment release, which is, we talk about a sediment spill. If we have a lot of sediment got into the stream in very short period of time, what will be the impact? So that is the key, process that we are interested in. So building on that project, we have, my collaborator has Dr. Dan, and his postdoc has done a lot of experiment in the laboratory to study the toxicity of these sediments on the freshwater mussels. So they have the paper published last year shows the impact of suspended solid to the juvenile freshwater mussels. They also have conducted experiment to look at the mussel or the sediment barrier, that impact to the mussels. So if you're interested in the toxicity part of the impact or what is this, how sediment would impact the mussels, I will refer you to read this paper. So on the same project, our group are looking at the sedimentation process and relevant to the hydraulics. So my students are involved in this project to develop a sedimentation models to predict where the sediments will end up with in the downstream that potentially have the impact or negative impact to the mussels. So the objective of our research is first to develop a model that can be used to evaluate the sediment impact in the future, right? And once the model has been developed, we need to validate it, otherwise it won't work, right? So we need to use the data to validate the model so that we know, okay, the model is actually did predict what we want. And after that, we demonstrate how to apply this model to study the Missouri stream and particularly about the mussel habitats and how can we use the model to help Missouri to better manage the freshwater mussels in terms of the sediment impact. And also we want to develop quantitative information and also tool to help help the engineering practices. So in terms of model objectives are quite simple. We try to make it a really, really simple model and to predict just two scenarios. So one is that if you know a particle size, so let's say we want to know the particular particle size, if that particle got into the stream at a certain flow condition, where that particle will be landed in the downstream. So what is the probability distribution of that particle will get into that downstream location. And scenario two is if we have the sediments have a distribution, okay? So we have different sizes of particles and then where they are going to be transported in the downstream. So what is the distribution in the downstream that these particles will be landed? And the one thing I want to mention that there's a lot of smaller particles will be suspended due to the turbulence. And all of these suspended particle will become a different impact, just like a suspended solid in the water, which also impact the mussels. So there's two different mechanisms over here. So in this study, we are going to develop a three-dimensional particle tracking model. So this model, we try to keep it simple so that we want model to be driven by just one-dimensional hydraulics. So in terms of input parameter, we just keep it as simple as possible. We just need three different parameters: flow velocity, depth average, the flow velocity, and water depth, and the particle size or sediment diameter. And these are the only input parameter that we need to put in a model, and the model will calculate the turbulence, calculate the flow, and calculate the sediment settling and the interactions with the flow. And in terms of output, we also want to keep it simple. We can keep just particle settling location. Okay, where does the particle will going to be settled? And in here, we're going to do a criteria to check if this particle will be suspended or not. If it is suspended, that means this particle will remain in the water and it will not, cause the bury of mussels. But however, there will be the mussel will be, feeling that suspended particles, so it's a sediment exposure zone for these mussels. If the particle does not suspend, it will settle, and that if you have enough amount of sediment, that will cause the bury. So that was the potential mussel barrier zone. And so we want to predict these two different mechanisms in this model. So this slide shows the equations that we use. These are governing equations for the particle tracking. And we have turbulence solver to predict the fluctuation of velocity in the water. We have a sediment drag model to calculate how fast the particle will settle. And also we have flow prediction to predict what is the flow distribution in the water column. So after the model been developed, we first validate the model. So we first validate the sediment settling velocity. So this is plot of settling velocity of sediments versus the diameter. So you can see the increase in diameter causes the settling faster. This is prediction versus measurements that we reported in the literature. So this slide shows the comparison between flow profile. So this is a velocity profile in different cases, and this is a turbulent profile and compare with the model. So this is a flume experiment, and this is just used for flow validation. And lastly, we also validate the particle distribution, if there's a particle released in the water. So this is an experiment conducted in the flume with this particle size range, and for that particular flow condition, I did not include the flow condition over here, but these particles will be distributed from about 1 meter all the way to 8 meters from the release point, and the peak is happening about a little bit over 1 meter from the release point. And this is a model comparison with the data, and they match quite well in terms of predicting the distributions of sediments in the downstream flume. And furthermore, we look at the differences between data and the model for different particle size ranges, from the smaller particle all the way to the larger particle. And you can see the model actually predict quite well in terms of comparison with the measurement data. So after that model being completed, we look at the particular case of a mussel habitat in Osage River, and this is the location that we are looking at. So at this location, this is the discharge as a function of time, and actually USGS conducted 2 field experiment at different discharges, and showing up over here. So they have velocity measured at these 3 cross section at Q1, and with a higher flow, they measured flow velocity at these 2 locations. So these data has been used in our model to drive the sediment transport. So we released 3 different classes, sediment size classes. So we call it fine, medium, and large. They follow log normal distribution. For fine particles, they represent limestone and silt. For medium particles, it's very fine to coarse sand, and large particles is from the medium sand all the way to the small gravels. So here are the predicted particle exposure zone. So where all of the particle will be touching the bed or interacting with the bed. So if you look at this 3 plots, shows the different particle sizes at Q1 condition. And you can see larger particles are closer, to the release point, which is 0 over here. And with decreasing of particle size, the further downstream will have, more impact by these, sediments. And of course, with these further in terms of distance, the concentration will decrease because the dilution effect over there. So if you look at the higher flow rate, the downstream distance will be impacted even further. So if you look at the Q1, for larger particles, most of the particles are like a 10 meter to 20 meters. And for Q2, we have extended to about 100 meters that impacted by the large particles. The smaller particles can go further downstream, and you can see for these really fine particle of 3 kilometers of water will, the mussel, if mussels are there, you will feel these particles. Okay. If you look at the particle settling, and a smaller particle will be washed downstream and settled even further away. But these larger particles in these 2 plots show the larger particles that are settled within very, very close to the release point. For example, Q1, they are most of them are settling within 10 meters. And for the Q2, that distance extended to a little further away. So that's just the one example, shows the model application. And you can see we still need a lot of field data to help us to build a model. So practically it's going to be difficult to model all of the streams for all of the flow conditions. So to generate this, we survey all of the, the 49 Missouri stream reaches with the sensitive aquatic species reported, and look at the USGS gauging station data. And we come up with this plot of discharge as a function of flow depths and the velocity as a function of flow depths. And for our model, we just need the velocity and the flow depths. So if we look at this, we can sample the flow condition by looking at the fifth, the medium, and 95 percentile of the flow, and come up with the three generic flow conditions. We call the slow, normal, and the fast flow conditions, so that we can use all of these conditions to represent the entire Missouri mussels habitats. So I just give you one example about the sediment barrier. And this is for the very fine to coarse sand with fast flow condition. And this is the flow depths that we modeled from 1 meter all the way to 12 meters. And for that fast flow condition, when water depth is 1 meter, this is accumulation of the particles, right? And then with increasing water depths, and with that flow condition, these sediment will accumulate even further to the downstream. With this, and we can look at the mussel barrier zone in terms of different key parameters. So we're looking at the mode, which is the peak of the particle will be located. Medium, which is the 50 percentile of the particle will be located, and the mean, which is just average of the particle will be located, and of different size range and different flow conditions, and for different depths, we can get the distance. So if we just count the particle numbers, they got into 100 meters, for all of these conditions. However, smaller particles contain less mass, right? Larger particles, think about if you have a small particle has, double its size, the volume increases by 8 times. So if you look at the mass, and the majority of the particle mass still remain in a little bit closer to the releasing point. So all of these conditions, even for the 12-meter water depths, this 20-meter range will probably the most concerned location in terms of mussel protection. Okay, so this is the medium and the mean. You can see all of these values. So this plot also shows the proportions of the particle will be represented. Will be get on the bed, settled in the stream. So I'm not going to go into the details of this, but I just want to pull back into this figure. This is still, although we simulate the slow, normal, and the fast flow, it's still very generic. And if you look at the prediction, we eventually got the particle size distribution can be represented by normal distribution quite well. If you look at the mathematical sense of normal distribution, just 2 parameters over there. It just one is the mean, the other one is the standard deviation. So if we can predict any condition, if we know the mean and the standard deviation, we should be able to come up with a theoretical prediction of the particle which will be located. So to do that, we implement a data-driven approach. So we first look at this is the potential water depths and the velocity that we're interested in the Missouri streams, and we put a grid in there. We just sample all of these, the potential combination of flow depths and the velocity, and we simulate all of these conditions. This is a physical-driven model. We end up with 41,600 simulations. And with all of these simulations, that we can train a machine learning model. So this is the whole bunch of analysis and model we trained. And I don't want to go into the detail of this, but eventually we come up with a tool that so-called sediment settling calculator powered by machine learning result. And with that, we just select which condition you are going to simulate. Just put water velocity, put water depth over there, and click that button. Within half second, we have a prediction result. And I want to mention, with this physical-based model, these take days to finish, and this within a second. So that we hope to give a tool that for resources manager to evaluate their project if they are interested in, knowing about these, particle location if there's a stream over there. So quickly, I'm going take home message. In this study, we developed a model that could provide quantitative information about sediment exposure and mussel barrier. And however, I want to mention there's model limitations because we try to make model as simple as possible. We implement the 1D hydraulics, semi-empirical equations. We ignore particle-particle interactions and also did not include the particle-induced density flows. And all of these physical processes that could impact the accuracy of the actual, sediment location and in the streams. And so that means if you really want to look at the engineering project, we need a specific parameters need to be considered. What is the actual sediment size, right? What is the density of the sediments? What is the stream condition that you're looking at? Because all of the equation that we use here are semi-empirical, may not be representing the real river situation. And lastly, if you really want to get more sophisticated understanding of what's going on in the stream and the particles, I would recommend, three-dimensional CFD model, which, you can do a little bit more analysis on it. So with that, I want to acknowledge the funding support from MoDOT and many collaborators from federal and state agencies that on this project. And also happy to take any questions. Thank you.
Well, thank you very much, Dr. Wang. Very nice presentation. So please, if you have any questions, put in the Q&A box and I will convey the questions. But before I look at them, so I have one quick question. So the sediment transport model that you are developing, would that only be applicable to soil particles, or if we're looking to microplastics or some pollutants, would that be applicable to the transfer of those in the water streams?
That's a great question. Yes, in general, yes. But this part of the modeling is just for sediments. We have a different suite model to predict other particles. For example, we developed a model to predict the invasive carp fish, the invasive carp eggs transport in the large river, Missouri River. And we also have a microplastic tracking model as well. And we're looking at that model right now and validating with some laboratory experiment and at this moment. And in general, this model can be used to predict any particles as long as we know the property of the particle, what's the density, what's the shape, what's the size. And then we can, modify the model to predict different particles.
And you were talking about, this is about point discharge, right? So it's a project happening along the stream somewhere and generating the sediments, as I understand. So would this model be useful to prevent the transfer of the sediments? So if we are if we're working on a project as a MoDOT, for example, can we look at this and say, okay, we need to slow down the velocity during this time to make sure that it's not going to cause a burial of a mussel habitat? Can this be used in this way?
I think it's possible. For example, this machine learning model that we developed, it's very quick. So compared to the physics-based model, you need to specify number and let it run, and over time it will converge, and then you can draw a conclusion. And from the manager point of view, if you want to design a optimized, parameter or flow conditions, and you probably need some, multiple trials, right? Because of trial and errors. But in here, you can really, for example, you can select the different flow conditions to look at, okay, this is what is the particle will be suspended, where that particle will be located. For example, this is like 100 meters. Is that possible? From engineering point of view, is that possible to relocate mussels, or should we design a different flow conditions to do the project? So there's a lot of different ways to do this. So the tool that we provide over here, just give a quick, although it's very simple, a lot of simplification over there, but it kind of give the resources manager a quick check. Okay, if I want to, like tweak the numbers, I can find out what might be impacted.
And this may be outside of the range of your research, but how about after the sediments settlement? Do the sediments move still after their first point of settlement, or is that a big issue for the mussel habitats or other species?
Yeah, that's I think that's still there's lots of debate, in terms of how sediment would impact mussels, because mussel has pretty good tolerance on the sediment because they live in the streams. Sediments is there anyway. So in terms of the resuspension and the resettling, the flow condition might change, and the stream condition will change. If you got into the area that has smaller velocity, and the suspended particle will settle in that location. So there's very complex processes, involved in this. It's very dynamic. So the modeling tool that we are developing over here, it is really simplified process, to give a quick overview of, what this particle will be, getting into the downstream. Because a really important question for the MoDOT is, for example, if we were doing the bridge maintenance over here, do we really need to care about 10 meter from this point or 100 meter from this point? Currently, there's no quantitative measures about where should we relocate the mussels, or should we relocate the mussels? A lot of these engineering practices is based on experience, and I know that they have a lot of collaborations with Department of Conservation, so they rely on their lot of experiences from these experts.
Very nice. So thank you very much again. I don't see any questions in the Q&A box, so thank you very much for your presentation, and thank you all the attendees for attending these presentations. Remember, this is recorded, so both presentations will be on our YouTube channel. And if you have any questions that you think of later, we will be happy to transfer them to the researchers. So thank you all for attending, and thank you, Dr. Wang. Thanks.
Thank you for having me.